Welcome to Statistics, where we bring complexity to clarity. I am excited to have you join me for our 20th unit CRD, that is Completely Randomized Design. Let's begin our journey of Completely Randomized Design, that is CRD. When the treatments are arranged randomly over whole of a previously determined set of units, the design is known as Completely Randomized Design or CRD. In CRD, the treatments are allotted to the experimental units entirely by chance without making any effort to confine treatments to any portion of the experimental material. Thus, the randomization gives every experimental unit in the experimental material an equal probability of receiving the treatment. The CRD is appropriate only when the experimental material is homogeneous. In field experiments, there is generally large variation among experimental plots due to soil heterogeneity. Hence, CRD is not preferred in field experiment. In laboratory experiments and greenhouse studies, it is easy to achieve homogeneity of experimental materials. Therefore, CRD is most useful in such experiments. Now, let's see how to prepare the layout of CRD. The layout refers to the placement of treatments on the experimental site. Suppose there are 3 treatments, namely A, B and C, and it is desired to repeat them 8 times. The experimental area is divided into 24 plots and the treatments are allotted to these plots at random. There is no restriction of assigning the treatments to plots. Here, since the number of units is 24, a 2-digit random number table will be considered and a series of 24 random numbers will be taken excluding those which are greater than 24. Now, let's see how randomization of treatments is done. Suppose the random numbers chosen are 4, 18, 2, 21, 14, 3, 7 and so on. Then after this, the plots will be serially numbered. That is, here you can see in the layout for completely randomized design with 3 treatments and 8 repetitions, there will be 3 cross 8, that is 24 plots. Hence, we have to number 1, 2, 3, 4 till 24 plots serially. Further, the treatment A will be allotted to the plots bearing the serial numbers 4, 18, 2 till 13, that is, the first 8 random numbers will be allotted treatment A, as you can see here in blue boxes. Then, treatment B will be allotted to the plots bearing the serial numbers 22, 1, 6 till 8, that is, the next 8 random numbers will be allotted treatment B, as you can see in pink boxes. Then the rest of the random numbers, that is 15 to 19, will be allotted treatment C, which you can see here in white boxes. Let's see the alternative method, that is cheat box method for randomization of treatment. Here 24 cheats are prepared bearing serial numbers 1 to 24. The first 8 cheats of numbers drawn will be the experimental plot numbers that will receive treatment A. That is 4, 18, 2 till 13 will receive treatment A, as you can see in the blue boxes. Then next 8 cheats drawn, that is 22, 1, 6 till 8 will be allotted treatment B, as you can see here in pink boxes. And the remaining cheats drawn, that is 15, 11, 24 till 19 will be allotted the treatment C, which you can see here in the white boxes. Now, let's see the statistical model of CRD, which is Yij is equal to mu plus tau y plus epsilon ij. for I is equal to 1 to up till t, j is equal to 1 to up till ri. Also, summation I is equal to 1 up till t ri is equal to n, which is equal to total number of experimental units, where Yij is equal to response of yield from the jth unit receiving the ith treatment. Mu is equal to true mean effect or general mean. Tau I is true effect of ith treatment. Epsilon ij is the uncontrolled variation associated with jth unit receiving ith treatment. Now, let's discuss the procedure for analysis of CRD in stepwise manner. The first step is calculation of correction factor, that is CF, which is equal to grand total square divided by R into T, where R is equal to number of repetition of treatments and T is equal to number of treatments. Step 2 is calculation of general mean, that is GM, which is equal to grand total divided by R into T. Step 3 is calculation of total SS, which is equal to double summation I is equal to 1 up to T, j is equal to 1 up to r, yij square minus cf. For our example, we can write it as y11 square plus y12 square plus y13 square plus up to plus y38 square minus cf. Because in our example, we have 3 treatments and 8 repetitions each. So till y38. Step 4 is calculation of treatment SS, which is equal to summation I is equal to 1 up to t yi dot square divided by r minus cf. It can also be written as y1 dot square plus y2 dot square plus up till plus yt dot square divided by r minus cf. And for our example, we can write it as y1 dot square plus y2 dot square plus y3 dot square divided by 8 minus cf, because there are 3 treatments and 8 repetitions. Step 5 is calculation of error SS. Error SS is equal to total SS minus treatment SS. Step 6 is to calculate treatment mean square, that is MST, which is the ratio of treatment SS to the treatment degree of freedom. Step 7 is calculate error mean square, that is MSE, which is the ratio of error SS to error degree of freedom. And step 8 is calculated F, which is equal to the ratio of treatment mean square to the error mean square. Now let's see the next step, that is step 9, which is prepare ANOVA for completely randomized design with equal replications. The ANOVA consists of source of variation with treatment, error and total. The degree of freedom for treatment is t minus 1, for error it is t into r minus 1, and for total it is rt minus 1. The sum of squares, that is SS, MS and calculated F, are computed using the formula as discussed in step 3, 4, 5, 6, 7 and 8. Or it can also be computed by the formula which is given here. Here, this term indicates correction factor. Now, the interpretation can be given as if calculated F is less than table F at 5% level of significance and treatment DF, error DF, then observed difference is non-significant and H0 is accepted, that is, all treatment means are equal. And if calculated F is greater than equal to table F at 5% level of significance and treatment, error degrees of freedom, the observed difference is significant. Hence, H0 is rejected, that is, at least one pair of treatment means are significantly different. Further, step 10 is calculation of SEM, that is standard error of mean. SEM is equal to root of MSE divided by R. Step 11 is if treatment F is significant, then we have to calculate least significant difference LSD or critical difference CD. where LSD or CD is equal to T at 5% level of significance and error degrees of freedom into root 2 into SEM. Step 12 is calculation of coefficient of variation, that is CV% is equal to root MSE divided by general mean into 100. Now let's discuss the analysis of CRD with unequal replications. Here steps 1 to 8 remains the same and step 9 is prepare ANOVA for completely randomized design with unequal replications. Here the ANOVA table consists of source of variation, which includes treatment, error and total, and degree of freedom for treatment is T minus 1. For error it is summation I is equal to 1 up to T Ri minus T, and for total it is summation I is equal to 1 up to T Ri minus 1. The sum of squares, that is SS, can be calculated by the given formula. For treatment SS, the formula is summation I is equal to 1 up to T yi dot square divided by Ri minus double summation I is equal to 1 up to T j is equal to 1 up to Ri yij whole square divided by summation I is equal to 1 up to T Ri. And for total SS, it is calculated by the given formula. The error SS is calculated by subtraction, that is total SS minus treatment SS. MS is calculated by SS divided by degrees of freedom, that is MS for treatment will be treatment SS divided by treatment degrees of freedom, and MS for error will be error SS divided by degree of freedom of error. Calculated F is the ratio of MS of treatment to the MS of error, which is calculated in the usual manner as we have discussed in previous steps. Also, the interpretation for CRD with unequal replications is same as that of CRD with equal replications. The next step is step 10, that is calculation of SEM, that is standard error of mean. SEM is equal to root of MSE divided by R0, where R0 is equal to number of treatments divided by 1 upon R1 plus 1 upon R2 plus up till plus 1 upon RT, where R1, R2, RT are the number of observations for different treatments respectively. Step 11 is to be done if treatment F is significant. Then calculate least significant difference LSD or critical difference CD, where LSD or CD is equal to statistic T at 5% level of significance and error degrees of freedom into root 2 into SEM. Step 12 is calculate coefficient of variation, that is CV% is equal to root MSE divided by GM into 100. Now let's discuss advantages of CRD. Layout is very easy. There is complete flexibility in this design, that is any number of replicates for each treatment can be taken. Whole experimental material can be utilized in this design. This design yields maximum degrees of freedom for experimental error. The analysis of data is simplest as compared to any other design. Missing observations creates no problem in analysis of data. The analysis is carried out in the usual manner, neglecting the missing plot as if it was not there in the experiment. This does not break any assumptions or rule of analysis of variance. CRDs are specially suitable in situations where an appreciable fraction of units is likely to be destroyed during experimentation or is likely to fail to respond. Now let's see the disadvantages of CRD. The design is suitable for small number of treatments. If it is difficult to find homogeneous experimental units in all respects. CRD is seldom suitable for field experiments as compared to other experimental designs. Thank you for joining me on this journey through our 20th unit CRD. If you found this unit helpful, don't forget to like, share and subscribe to Statistics for more insights and clarity on statistics. Your support helps us continue creating content that makes complex topics simple and accessible. Follow us on Instagram and LinkedIn.